Sounds good. So I'm just going to go ahead and introduce our speaker today. I'm very excited that you accepted to give a talk in the seminar series. We have Dr. Jae-sun Seo, who is an associate professor at the School of ECEE at Arizona State University. His research interests include efficient hardware design for machine learning, neuromorphic algorithms, and integrated power management. He was the recipient of the IBM Outstanding Technical Achievement Award at 2012, the NSF CAREER Award at 2017, and Intel Outstanding Research Award in 2021. Thank you again for accepting to give the talk, and I'm excited to listen to the talk.
Thank you very much, Ramtin, for the kind invitation and the introduction. So thank you all for joining this seminar, and today I'll present our recent work on SRAM-based in-memory computing for energy-efficient AI systems. So as you know, with the waves of AI, there has been many custom chip accelerators to efficiently execute deep learning and deep neural network workloads from major industry players, many new startups, as well as academia driving more crazy things. In these digital based deep neural network hardware inference accelerators, we actually noticed that there are many computations that need to be done to execute like one DNN model. However, to do the computation, we have to move and load the memory data to where the computation actually happens. And in this recent paper, they are comparing how much it takes to do like a multiplication for different precisions, as you can see, versus depending on the memory size and how far it is from the where compute happens, how many picojoule it takes to actually get the data to where the compute happens. And you can easily see in this log scale that the data access and communication energy can easily dominate the overall energy. So these have been also verified in some of the chip measurement data in the literature. So you can see from these three representative digital accelerator chips that more than 2/3 or higher percent of them are dedicated to like the scratch pads, activation banks, weight banks, accumulation buffer, which are all different types of memory access in the overall hierarchy. And this becomes a dominant portion of the total power or energy consumption. To alleviate that, recently there has been a number of works that tutored so-called in-memory computing. So in conventional all digital, as I kind of alluded to, there is a memory hierarchy, and let's say in a global buffer and local buffer, there are weights and activations stored in SRAM, RM, different memory, and then you first have to read this row by row, put it in a line buffer, and then eventually convey that, communicate that also to a separate compute engine that is physically apart. In the newly proposed in-memory computing paradigm, we're trying to turn on multiple or even all rows of a subarray simultaneously. And by doing that, we can actually do these dominant multiply and accumulate operations inside the memory, for example, along the bit line in an analog manner. So by doing this, we can largely reduce the data transfer because we don't really need a separate MAC array. We're actually doing the MAC array inside the memory. And by asserting multiple or all rows together, we can definitely exploit increased and enhanced parallelism. So due to these, there's large potential for energy efficiency, but there has been key challenges, namely where, digital is obviously good for high noise margins. When we go to analog or mixed signal, there's variability concerns that might affect DNN accuracy and also large-scale integration of these new custom designs. Just to set up the stage, when we talk about in-memory computing, there can be different memory technologies and devices. So in SRAM, DRAM, and different emerging non-volatile devices such as RMPCM, these are a very high-level summary of the advantages and challenges for each of those memory devices. There can be more detailed explanations in different papers. In SRAM, obviously, SRAM is going to be there for any given technology. So 7 nanometer, 2 nanometer, you name it, it's going to be tape-outable. SRAM obviously has a very high on-off ratio. It's reliable. It has decades of experience in large-scale integration. The challenge is that typically, the off-the-shelf 6T SRAM are push rule based. So like the foundry engineers kind of, really customized it to be really dense. But as we need to employ at least a couple more transistors to enable in-memory computing in a reliable manner, those custom designs with a couple new devices or discrete components, the push-pull design might not be openly available. They need some collaboration with foundry, which are not always readily available. And because we're adding a couple more stuff, the bit cell becomes a little larger, array larger, and so on and so forth. DRAM obviously stores much more data than SRAM, so doing in-memory computing on the DRAM side could significantly reduce the DRAM communication. However, the 1T1C DRAM, the read is destructive, so once we do some kind of read, we have to write again. Obviously, there are like 2T1C, 3T1C type of designs that don't make read destructive, but modifying these bit cell and array is very difficult in standard DRAM process. Then we have these non-volatile RM and PCM that has much higher density than SRAM at the bit cell level. However, the peripheral circuit still might be large, so at the array level, have to check really how much area benefit there is. And compared to SRAM, the on-off ratio is low, and these are not necessarily available in all CMOS nodes, and large-scale integration still needs a lot of verification. So to these reasons, in this talk, we will focus on SRAM-based IMC design since it's most robust and viable for large-scale integration. So SRAM IMC designs in these analog mixed signal in-memory computing, we can try to categorize it into two categories, namely resistive IMC and capacitive IMC. So in resistive IMC, we're trying to use transistors to pull them down or up at the same time simultaneously by turning on multiple rows together. So let's go step by step from the bit cell. So in this TSMC work from ISSC 2020, they're doing basically an AND operation within a bit cell. So only when input that drives the word line and the weight that is stored in the bit cell are high, then they're going to pull it down, and every other thing, they're just going to let the BL float from the pre-charge voltage. In one of our work, XNOR-SRAM, we actually utilize both the pull up and pull down, and we try to do XNOR operation within a bit cell. So only when input and weight are at the same polarity, then we're going to pull up at this case and at this case. And if they are at different polarity, then we're going to pull them down by both PMOS and NMOS. So by doing it this way at the bit cell level, and if we connect these bit cell at the same column all together, and let's say we turn on all the rows, then we, in this TSMC work, we can get something like we have a pre-charge device, and then we have a number of parallel pull-down devices, and depending on what happens with the input and weight, it will determine how many of them are going to get pulled down. Similarly, in our XNOR-SRAM work, we have an RBL in the middle, and out of, let's say, 256 bit cell in the column, how many of them are going to get pulled up to VDD, how many of them are pulled down, so we get kind of a resistive divider. But this could have some crowbar current, this could have some time dependency, so there are different trade-offs. But still, if we turn on n rows, basically we can perform an n input dot product or MAC operation in a single cycle. And depending on the number of pull down and pull up cells, we basically have a monotonic relationship between the mathematical MAC result and the RBL voltage, as you can see here for both these works. On the other category of capacitive IMC, we either try to use charge sharing or capacitive coupling. So in this Princeton work, they use this 8T1C or 9T1C. Actually, there's another transistor at the array level, but basically weight is still stored here, and then the input activation is going to drive these additional two PMOS transistors, and either of them going to be multiplied between the differential weight storage on the left and right node and the differential input activation here, and the result of that XNOR operation is going to be stored in this capacitor in either VDD or 0. In our work called C3-SRAM, we actually have a different bit cell design where we have a series capacitor. So the weights are still stored inside the SRAM bit cell. We have this multiplication MAC word line and MAC word line bar. So we have these driving the gates of these two MS passgates, and depending on what the word line value, the input activation are, this VC will drive this NBL through a capacitive series capacitor. So when we put together n bit cells together, then what happens in this Princeton work is that some of the capacitors, depending on the bitwise multiplication results, is going to have, you know, discharge to 0 or charge up to VDD. And if we just connect them all together, then it's going to settle down in somewhere in the middle, and that analog voltage will represent the MAC results. In our C3SM work, basically similar to the resistive divider work in the previous slide, we basically implement a capacitive divider work through these series capacitors. So depending on what VC is driven with, it's either going to get coupled in between MBL and VDD or MBL and VSS. And depending on how many of them are at the upper side or lower side, this MBL is going to be kind of a direct relationship between the MAC value. And you can see, compared to the previous slide for both Princeton and our work, due to the nature of the capacitor, whether it's charge sharing or capacitive coupling, we basically have a much more linear relationship, which is certainly good. One thing to point out is that, let's say we did this kind of resistive or capacitive AMC and you saw these bit lines came into like an analog voltage value. We have to, you know, convert that back to some digital values, which is why we need an ADC typically for any IMC designs. I want to just point out that ADC optimization is actually very critical for IMC. So in one of our journal papers, we basically, for example, swept the level of flash ADC levels. So like 8 level is a 3-bit ADC, 16 level will be a 4-bit ADC. And you can see that we're trying to, you know, these gonna saturate at some point, and we're trying to pick the design points at the inflection point here. One thing I want to point out is that it depends also on which kind of ADC design you use, like a flash or SAR ADC. In these works, we use a flash ADC. Couple things to point out is that in the resistive IMC work, we had these kind of nonlinear relationship, although monotonic, between the MAC value and the RBL. And there's two ways of doing the quantization. Let's say we have this 11 level design point, then there are a couple different ways. We can either just, you know, we know that there is a minimum range and a maximum range from the mathematical MAC computation point of view. So whatever that min and max range is, we can just equally divide that into the number of levels we selected, and that will be the linear quantization. That's not necessarily good because you see here that, you know, from the actual neural network data, there's hardly any data at the very near the min and max, and most of the data are in the middle here. So there's two ways to exploit this. One way is doing the so-called nonlinear quantization. So there are several algorithms for that. Basically, we're trying to put more fine-grained reference level where there's more data. So you can see that where there's more data, the, you know, delta between the reference levels become more fine-grained, and then we will have kind of this one-to-one relationship between the reference level and the flash ADC reference voltages, as you see here. The other way is doing a clipped linear quantization. Here, we just select a range like plus minus sigma or plus minus 3 sigma where most of the data resides. And then within that range, we still do linear quantization. And in this case, it happens to be that the slope of the transfer curve in this resistive IMC design is pretty steep in the middle where a lot of data is. And that actually results in, you know, the smallest delta in where the most critical data is, which results in very small delta Vref between adjacent reference voltages of the flash ADC, which makes it more subject to offset and variability. In this case, actually, it happens to be that we were able to increase the delta Vref where most of the data resides. So this becomes more relaxed kind of offset requirement and actually results in better accuracy, as we can see here for like the binary activation or ternary activation case. We could, you know, improve the CFAR10 evaluation accuracy by at least several %. So these were the two initial single array, single macro prototypes that we fabricated and tested for the resistive IMC and the capacitive IMC. We were, for binary operations, we were able to get hundreds of teraops per watt with reasonable CFAR10 accuracy, and these has been in collaboration with Professor Minggu Suk's group at Columbia. So we first got these, like a couple conferences and JSSE papers, and then What I want to present in the remaining of my presentation is how we expanded these into several different directions. So, namely, first, this is a single macro, and obviously this is not gonna, cut the work for many large DNN models, let alone small models. So what we did is this, expanding these single macros, we built a programmable system-level accelerator that integrates more than 100 of these IMC macros. And another work is, as we saw, like ADC, precision and selection is one design parameter. I mean, there are many other design parameters. What's the optimal array size for the SRAM IMC from the system level point of view? So there are many design parameters that we actually need to optimize, and there's different amount of variability. So we actually built a modeling framework to optimize these. And then there's gonna be some accuracy degradation depending on the transistors and technology. And if we understand and inject some of these hardware noises during the training stage, then during inference, we can actually improve them. And then finally, we can actually try to exploit some of these hardware noise, which in some sense is not ideal for certain scenarios like the accuracy. But I mean, there are other kind of avenues like adversarial robustness. We actually try to see if this might be good, injecting some random noise so that the adversary will have a harder time to try to disrupt the network. So let's try to go briefly one by one. So in this, the name is PIMCA, Programmable In-Memory Computing Accelerator. This has been recently presented at 2021 Symposium on BLI-Side Circuits in June. So just want to point out that the trends on this IMC designs, obviously there has been single macro designs, including a couple from our group. Obviously people notice that this is just too small. We have to integrate it into a much larger system. So, several macros to tens of macros to hundreds of macros, and IMC total chip in this IMC size in the total chip ranging from tens of kilobits to, several megabit has been more recently published here, and we're going to focus on our work called PIMCA. So there has been some IMC systems, as I briefed in the previous slide, but there are some limitations, like there are certain non-MAC operations in many different neural networks, and either those are not supported, or other like pooling or residual specific operations are not well supported. So the motivation of our work was to propose a programmable IMC architecture. And for that, we built a custom ISA with some dedicated loop support control for the hardware. And we try to make it programmable for different networks, a couple different precision, and basically integrate a very large system that can fit DNNs for edge devices fully on chip. So this is the overall PIMCA architecture. So we expanded the C3 SRAM, the capacitive IMC one, a little bit more so that basically the pass gates are replaced with transmission gates for a more reliable operation, and we embed a 2.2 femtofarad MOMCAT on top of each bit cell. The macro is a 256 row, 128 column IMC SRAM array with a 4-bit flash ADC at every single column that enables a fully parallel matrix vector multiplication with this macro level design. And then we put together 108 of these 256 by 128 macros, totaling up to 3.4 megabit for the entire chip. And these 108 macros are organized into 6 cluster, where 18 IMC macros are within this PE or cluster. And the outputs of these are summed with a configurable adder tree, and we have additional 1.5 megabit activation memory, and we have a top controller governing the overall instructions and operations. This is the 6-stage pipeline where it integrates the custom in-memory computing processing. And one specific thing I want to highlight is that there's actually a bypass path between the activation memory and SIMD, because, for example, residual networks, there's some element-wise operations that don't really need matrix vector or dot product. So instead of going through this, we can directly bypass the activations to the SIMD stage for those element-wise addition. I talked about hardware loop control. So as you know, in DNNs, there are many repetitive and iterative computations. So we added two specific supports. Number one is just repeat a single instruction for a specific amount of times, like RP, and we can do this with the 6-bit category in the instruction, and the address will automatically increase in each repetition. The other is we added support for generic nested loop definitions by special loop instructions with dedicated counters and registers, and this will well support various convolution operations. It's not necessarily doing the same thing over and over again, but it has a very specific nested loop pattern that it has to go through. And by leveraging these for like a VGG9 network for CFAR10, we were able to reduce the total number of instructions by about 4x by using these loop support control. So this is the 28 nanometer prototype chip where we integrated these 108 macros in this 5.9 millimeter by 3.5 millimeter relatively large test chip. And briefly going over the measurement results. So this is the x-axis is the mathematical MAC result, and then the y-axis is the ADC output. So ideally, everything should be within this red box, as you can see here. Due to the hardware variability and noise, there are a couple of them, data outside of these red box, which is not ideal. But at least when we compare a single macro versus all the 108 macros, there's not that much there's not that much macro to macro variation, which is certainly good from the system level point of view. And then this is the energy efficient result where we report both single macro level, which is obviously high. But then the important point is when we put together all of these and include like the SIMD, controller and everything, then we try to report the system level peak energy efficiency across these different networks and precisions, and also system level average energy efficiency when we run all these networks from beginning to end. So obviously the average energy efficiency is going to be lower, but still, we're able to achieve, hundreds of teraops at the system level, which is important. So comparing to the system level IMC works that I mentioned in one of the previous slides, ours is one of the largest integration in terms of scalability, and also we achieved one of the highest system level energy efficiency for binary operations, 437 TOPS per watt, and also reduce noticeable reduction for energy per inference compared to one of the previous works. How are we on time, Ramtin? Maybe another 5-10 minutes or?
Sure, of course, yes.
Okay.
Yes.
So briefly, like to just touch base on the 3 remaining works. So in the date 2021, we presented this modeling and optimization framework. So in here, I'm actually utilizing some of the hardware data that we had from the XNOR-SRAM C3 SRAM chip. So here we can do, depending on how much noise, mismatch, ADC offset we have, and then we're trying to, decide the optimal quantization range. We talked about like the, clipped linear quantization. So when we clip it, what will be the optimal range to clip? And then how many rows should we turn at the same time? What should be the ADC precision resolution, all these things. So you can see that depending on different variability we have, actually different, optimal points have been selected for quantization range, which will result in different accuracy. So we can try to characterize these. We try to open source the gist of these things, and then when we validate it across the actual chip measurements, although it is somewhat more conservative, we can get pretty similar trends and relatively close accuracy, which is good for some quick and first-hand analysis when we try to decide these different parameters. And next is about accuracy improvement. So this is under revision for IEEE design and test. But the thing is that, as I showed you, even in the PIMCA chip results, I mean, in our previous work and other people's work, you can see that the mathematical, MAC result versus what we get at the ADC output is not a thin straight line, and there's going to be some variation inevitably in these analog approaches. So, and these can result in notable accuracy loss And some work around it is that if you try to turn on too many rows at the same time, you're subject to more variation. So maybe they have to reduce the number of rows that turn on. But this is going to adversely impact the parallelism and energy efficiency. So what people have tried in the past to actually employ some of these hardware noise, because we know that we're going to run this inference in these noisy hardware. So can we incorporate some of these noise characteristics during the training process? And there has been a number of works, but some of them have some of these deficiencies. Either they incur large area overhead, only evaluated in small data sets, only turn on small number of rows, still, considerable accuracy loss, or they mostly try to inject noise at individual weight levels without considering like the crossbar IMC structure or the ADC quantization that will happen in the hardware. So considering those, we try to look into our own, macro level chip measurements. And then while people try to fit it mostly in the Gaussian, we actually noticed that it doesn't really fit well in a single Gaussian thing. And then depending on the MAC value, the noise profile can be different. So in considering these, what we do is that we divide like a very wide MAC that will happen in a deep neural network. We divide that into an n input MAC where n corresponds to the number of rows that turn on at the same time, or basically the number of rows in this SRAM IMC crossbar. And then we actually consider the quantization of the partial sum by the ADC during the training process. So once we consider these during the training, when it tries to go through similar things during inference, we're expecting that, when we don't do anything during training and just do inference, we're all subject by these noise, but we're trying to recover as much as possible by this IMC noise-aware training. And these seems to be working pretty well to some degree. So we tried a bunch of experiments across different models, different precision. Even we characterize a test chip across different noise, like supply voltages, which will have either higher noise or lower noise. And you can see that we do like conventional IMC inference, which is we don't do anything in the training. We can just do ADC quantization aware training, and then we can on top of that add the measurement noise, and we can see that the yellow bar consistently outperforms all the other approaches. And actually, one better thing is that when the noise is higher, we actually get more improvement compared to conventional approach. And we can do the same thing for the C3 SRAM. Previous slide was the XNOR-SRAM IMC chip. So not only just one of the specific macros, but across resistive and capacitive, we can see that this generally seems to work well. And finally, wanted to talk about this recent paper that will be presented at 2021 DAC, where we're trying to leverage some of these hardware noise for adversarial robustness improvement. So it has been well known that there are these adversarial attacks that can be done at either like for computer vision applications, just change a little bit of pixels, add some unnoticeable Gaussian noise, and then it will flip the classification result drastically. Or somebody can try to adversely just flip some of the weights, and only by flipping a small number of weights, these works have shown that the accuracy can be tanked to random estimation. So there has been some prior works to improve some of these adversarial attacks. So there has been some algorithm work, some hardware works, but some of the notable drawbacks is that if we concentrate on, we want to run this on some hardware, the noise are not specific to the actual hardware, and especially for IMC, they haven't quantized them at the crossbar level, or they use even just only synthetic or Gaussian noise distributions, which we saw that they might not be really correspond to the real hardware, and some of them have quite some redundancy. So in our proposed work, we tried to, improve the adversarial robustness by similarly injecting noise from the actual IMC chips that we had during the training process, and we also try to aggressively quantize the partial sum that might, make the results more coarse-grained, and then some of these very fine-grained perturbations that the adversary adds might be masked by these quantizations. So these are some of the highlighted results. So you can see that there are two ways of training this. We can do without adversarial training, and we can do some adversarial training. The takeaway is that by doing this, the overall accuracy level will be improved. But if we compare whether we do the non-adversarial training or with adversarial training, the IMC training, the noise that we do during the training process where we inject the IMC chip noise, consistently outperforms, whether we do it without any, inference, and it, improve the PGD accuracy by almost 10% here. In summary, I try to cover, quite some, recent works here, but hopefully they can, sit in the overall picture that I have been envisioning too. So several years ago, we started off from the single macro IMC designs. We were really, intrigued by these resistive and capacitive IMCs that can demonstrate hundreds of teraops per watt, really improving the energy efficiency. And we can demonstrate the macro level, but there are many things that has to go beyond a single macro design. So we, taped out and measured this PIMCA chip that integrates a very large number of IMC macros in a single chip. We also try to, propose a modeling and optimization framework to, optimize all these design parameters and try to improve the accuracy, as well as enhancing the adversarial robustness by injecting some of the IMC noise that we grab from the actual IMC chips here. And finally, I would like to acknowledge my collaborators from Columbia and ASU, Minggu Sok and Dalian Fang, and many of my students who have either graduated or still working well with me, and other students from Columbia as well. And finally, my sponsors, NSF, Samsung, SRC, and the JUMP Seabrook Center that has been also sponsored by DARPA. Thank you very much, and I'll be happy to take any questions.
Thank you so much. Very impressive work.
Thank you.
Nice. I do think we have some questions. First of all, thank you. Great talk. Very impressive work, especially going all the way to the chip design. We know it's not an easy thing to do. So I'm gonna look at some of the questions that we have here and pick. Actually, we have some questions from 1%, so let me see if I can choose some of them. So one of the questions is, how efficient is the accelerator? I mean, probably in terms of energy efficiency compared to SRAM-based IMC architectures. Have you done any direct comparison with SRAM or not?
That's a good question. We also have done some SRAM IMC work. I didn't include it here because I wanted to just make it, unified across the SRAM designs. But in short, so if you look into the literature, I would say, there are not that many system level RMC designs. There are still, a number of RMC single macro designs, which we also have done. But if you look at the TOPS per watt numbers, I mean, at the same precision, still the SRAM IMC designs have higher energy efficiency. There are a couple of reasons, but one is that in many of the commercial RRAMs, I mean, the current consumption and the energy consumption is dominated by these, high conductance or low resistance states, LRS, and those, low resistance states, the resistance is actually pretty low, like, tens of kilo ohms, several kilo ohms. So that means that when they, although the density might be good, when you have to utilize all those LRS states, then the accumulated current will be really high. It might be much higher than SRAM, and that's one of the main reasons why the RRAM energy efficiency, I don't think there's many designs that, report like hundreds of teraops. They're all improving, but at the same time, on SRAM side, nowadays there has been more than 1,000 teraops for different precisions. So.
Makes sense. So we have another question which I'm also interested to know how it is happening at the chip. The question is, when we have different I'm paraphrasing what I'm saying here. So having different macros, I assume that when we go from larger scale workloads, when we want to deploy them on different macros that are smaller sizes, is there any NOC or any involved to communicate between different macros, implementing, for example, one large matrix? Or
yeah. So that's a good question. Yeah, so there are, different ways to do it. And then, for example, if you, so for example, if you look into, sorry. Yeah, if you look into maybe like one of these works, like the Princeton work, they try to employ some kind of network on chip so that they can communicate with different computing and memory macros. We didn't have a conventional NOC, but we had we basically had the PE to communicate with the SIMD, and we basically broke down the job of the networks into these macros, and then had the SIMD to take care of the rest of the accumulating operations. So in a sense, we certainly have some communication interface between these PEs and the SIMD in the middle, but it was customized for our own needs. But it's correct that when you have many macros, you need some kind of on-chip network or on-chip communication interface to go back and forth between these.
Okay, thank you very much. I also have a question, so I see some question, but I just want to use the privilege of being the organizer to ask my question.
Sure.
So when in the adversarial part, you mentioned that you leverage the variations within the chip to do the training. Does that mean that the chip itself is within the training loop, or we are somehow extracting those variations and mathematically modeling them?
Yeah. So it's a latter. We are not really running these things, using our chip during training, but what we did, kind of similar thing for the adversarial work, just using these slides here. So we extract these measurement results. So we know the noise profile, depending on what the partial MAC result is, we know what we're going to expect. So we kind of basically have like a lookup table. So let's say if the MAC, computation mathematically should be -20, then we know that out of 80% of those -20 results is going to have ADC output of 5, maybe 10% will have 6, 10% will have 4, something like that. So we have this probability table, and then we kind of train with those lookup tables, and then during the inference it will go through a similar noise profile. So we're having the network train with this pre-characterized extracted measurement results, and then have the weights correspond to that, which seems to help the inference, and it seems helping us in the adversarial robustness as well.
Sounds good. Yeah, it does make sense. So let me go to the audience here. Do you have any questions that you want to ask? Yeah, go ahead. So the last question. I'm going to repeat the question.
Sure.
For example, you could open the full layers like activation function, the same chip.
So I think the question is, again, I'm paraphrasing it, are there the non-matrix vector multiplications are also implemented in the same chip? I believe that you mentioned that it is there when we're talking about the CPU, but maybe you can explain.
So the question is about what kind of non-MAC operations are supported in the chip?
Yes. Are they within the same chip or?
Yeah. So basically, for any, variants of ResNet architectures, this is not supporting any given, neural network out there, but some for basic like VGG, ResNet. These variants of architectures can be supported. Max pooling, batch norm. Those are all supported in the SIMD engine. So the SIMD engine has many different operations and instructions that can support these type of max and pool, compare, element-wise add, these things. So, you know, all the operations that are necessary for inference of these DNNs are supported on chip.
Thank you so much. So I'm probably gonna get more questions later, and I will reach out to you. I can see that we have some other questions, but
sure,
I can put them together and ask you again. Thank you very much for the amazing work you did. Thank you for the talk. You covered a lot of different interesting topics. So thank you for your time, and thank you for agreeing to give a talk. Once again,
thank you so much. Thank you for the attention.